Okay, in the last class we were discussing two figures of merit. One is the value utilization factor and the other one is transformer utilization factor. Both these factors have to be minimized. So, let us say how to choose these values for a given value of pulse number. So, if I try to recall what was the expression for the transformer utilization factor TUF, the expression is pi by under root 2q sin pi by q. So, TUF is dependent only on q and q is a positive integer greater than or equal to 2. Okay. So, that is what we have been restricting the value of q to. So, one can see that TUF is minimum when it is equal to 3. So, what I will do is I will try to give the value of TUF for different values of q. Suppose I take different values of q and also get the values of TUF. So, the first value of q is 2. So, for q is equal to 2, TUF can be calculated, it is 1.571. For q is equal to 3, just substitute in the expression 1.481. For q is equal to 4, it is 1.571. For q is equal to 5, it is 1.690. Q is equal to 6, it is 1.814. So, we see that it can be verified by substituting different values of q. What is the value of TF? So, q is equal to 2 gives 1.571 and the next value of q, that is 3, gives a lower value. Then after that a higher value of q gives a higher value of TF. Now, as q increases, the value of TF continues to increase. This can be verified. Okay. So, the optimum value of q is 3. So, q is 3 is something which is a coincidence, because our AC systems all are 3-phase systems. Okay. So, we can say that P should be a multiple of 3. Now, this is only based on TUF. See, please note this result is applicable based on TUF. Now, we have to verify whether the value utilization factor will give a different choice for Q and hence a different choice for P. Okay. So, sorry, this is based on TUF. Okay. So, if the pulse number P is equal to say 3, then this means the optimum values of Q, R and S are Q equal to 3, R equal to 1, S equal to 1. Okay. Now, let us just make our choice by taking this value of 3 which is obtained based on TUF. So, if I say based on TUF P should be a multiple of 3, the first possible value of P is 3 itself. The second possible value is 3 into 2. Okay. Suppose P is equal to 6, then the question is what should be the value of Q, what should be the value of R, what should be the value of S. Now, the only hint we have got so far is for the value of Q. So, there are, I mean we saw that Q should be a multiple of 3 based, that is based only on TUF. So, either it can be equal to 3 or equal to 6, okay. But still we should not rule out other choices for Q, because this result of P being multiple of 3 is only based on TUF, it is not based on the other utilization factor. So, let us try to consider all possible choices. So, all possible choices of Q, R and S, which will give a P equal to 6. Okay. So, let us form a table. So, I will try to show all possible cases which will give me P equal to 6. So, I will try to consider different values of Q, R, S and such. I mean, these values are such that the product of these 3 values is equal to 6. So, my intention is to get P equal to 6. Okay. So, let us see for the different choices of QRS which will give P equal to 6, the values of value utilization factor as well as transformer utilization factor. So, how many possible choices are there for Q, R and S for this given value of P, which is 6? So, 6 choices. Let us see. What are the possible choices of Q? See, Q has a constraint, it should be greater than or equal to 2. Okay. So, Q is always greater than or equal to 2, R and S are greater than or equal to 1 and all are integers, all are positive integers. So, let me take the least possible value of Q. Now, please note I am taking Q equal to 2. This is because the earlier result of Q equal to 3 was only based on TUF. Okay. So, if Q is equal to 2, then I can have R equal to 1 and S equal to 3, so that P is equal to 6. Or I can also have R equal to 3 and S equal to 1. Okay. Now, these are the only 2 cases with Q equal to 2. The next possible value of Q is 3. So, if Q is equal to 3, then the possible values of R and S 1 and 2 or 2 and 1. So, 3 1 2, 3 2 1. Any other possible value of Q? 6. So, if this Q itself is 6, R and S should be 1, so that P is equal to 6. So, these are the only 5 possibilities for P is equal to 6. So, for each of these 5 possibilities, let us see what is the value of VUF, what is the value of TUF. So, I will just give the values, we have the expressions. So, this is 1.047, 1.571, 3.142, 1.571, 1.047, 1.481, 2.094, 1.481, 2.094, 1.814. So, if you look at the last 2 columns, these 2 columns give the values of the 2 figures of merit that we are trying to minimize. So, if you look at the value utilization factor, the least value of value utilization factor occurs for 2 cases. The least value is 1.047. So, 1.047 is occurring for Q equal to 2, R equal to 1, S equal to 3, and it also occurs for Q equal to 3, R equal to 1, S equal to 2. Now, if you look at the transformer utilization factor, that is the last column, again there are 2 cases in which TUF is minimum. The minimum value 1.481, there are 2 cases. Now, the 2 cases for which minimizes VUF are not the same as the 2 cases which minimize TUF, but there is one case with Q equal to 3, R equal to 1, S equal to 2, which minimizes both VUF and TUF. So, obviously, this is the best choice for Q, R and S for the given value of P, that is 6. Okay. So, now let us say what is the circuit for Q equal to 3, R equal to 1, S equal to 2. So, I will try to draw the circuit only for this case. So, we are not interested in the other cases because they are not resulting in optimum values of the 2 figures of merit. So, from now on, when I consider p equal to 6, the only possible values of q, r and s are 3, 1, 2 respectively. So, let me try to draw the circuit. Okay. So, for the sake of simplicity, what I will do is I will draw the voltage source. I will show a voltage source in the circuit diagram, though we know that in practice the voltage is obtained as the EMF across a transformer winding. Okay. So, q is equal to 3, r is equal to 1 and s is equal to 2. So, this is the same as the case that we saw which minimizes VUF and TUF. So, there are two commutation groups, basic commutation groups that are connected in series. S is equal to 2 means two commutation groups connected in series. Since R is equal to 1, there is only one parallel path. Okay. And in each commutation group, there are 3 thyristor valves or 3 voltage sources. So, if I try to draw the circuit diagram, so this is one commutation group. There is one more commutation group connected in series with this. So, I bring out 2 terminals which are the terminals of the DC side and the voltage across this is V. Okay. So, let me give some name for these thyristor valves, but before that let me try to give the expression for the voltages. Okay. So, suppose this voltage is EM cos omega OT. Now, if I take one commutation group in which there are 3 sources, the voltages should be displaced by 120 degrees, 2 pi by 3, that is 120 degrees. So, this voltage will be EM cos omega OT minus 120 degrees, and this voltage is EM cos omega OT plus 120 degrees. Now, there is one more basic commutation group. There are 3 sources in that commutation group as well. So, the voltages of these 3 voltages in the second commutation group also are displaced by 120, but these voltages are not in phase with the original voltages, that is the voltages of the first commutation group. So, what will be the voltage of the voltage source in the second basic commutation group? Let me take the first voltage source. Of course, the peak values are all same, EM plus pi. Say, if I have 6 sources in this circuit, I have 6 sources. So, if I want a waveform which is close to ideal, see our ideal waveform is always a constant voltage for the DC side voltage Vd. See, Vd is having a desirable voltage which is constant. Now, I can't achieve constant voltage, but I can achieve the best possible waveform for Vd. So, if I want to do that, what should be the phase angle difference between the 6 voltage sources? 60 degrees, it is 360 by 660. So, I should select the phase angles of the voltages of the second commutation group such that the phase angles of the 6 voltages are displaced by 60 degrees, but still if you take the individual basic commutation group, the phase angle difference is 120 degrees. So, what should be the voltage of the first voltage in the second basic commutation group? Em cos omega ot minus 60 degrees. Then the second voltage is Em cos omega ot minus minus 180 degrees. And the third voltage is Em cos omega ot plus 60 degrees. Okay. So, let me give some names for some of these voltages. Suppose I call this voltage as EA. See, this A, B, C are letters used for the 3 phases. So, E with a subscript A means A phase voltage, I mean one can say that. I will call this as EB. And this is EC. Now, I will not give a special name for the next voltage, that is in the second commutation group. There is a voltage Em cos omega ot minus 60 degrees. Now, can I write that in terms of one of the notations EA, EB, EC? Can I write it in terms of the already used notations EA, EB, EC? Okay, that is one way of doing. But okay, let me go to the second voltage, Em cos omega ot minus 180 degrees. Can I say that is minus EA? So, this is minus EA. Okay, I will come to the first voltage. This is minus EA. Now let us come to the first voltage, Em cos omega ot minus 60 degrees. Can I write that as negative of some already used notation? Minus EC. So, this is minus EC. And Em cos omega ot plus 60 degree is minus EB. So, this is minus EB. Now, I will try to do some manipulations by just altering the positions of the thyristor and the voltage source. Say, when I have a thyristor connected in series with a voltage source, okay. So, as long as it is a series connection, if I interchange the positions, the circuit working will not change. See, if there are 2 components connected in series, if I interchange the positions of the 2 components, the circuit still performs in the same way. Okay. So, what I will do is, I will try to slightly alter the circuit. Okay. So, I will say that this is equivalent to, so I will draw one more circuit diagram. So, this is the first basic commutation group. The voltage here is EA, the voltage here is EB, the voltage here is EC. So, I will give some names for the thyristor valves also. I will complete this diagram. So, suppose I call this 1 thyristor valve 1. Now, I will go to the next voltage waveform which is immediately lagging EA. So, it is not EB, it is minus EC. Say the phase angle of minus EC is minus 60. So, I will call this thyristor as thyristor valve 2. Okay. Then the next voltage is minus 120. The next one which is lagging minus EC is EB. So, I will call this 3. Okay. Then the next voltage which lags EB is minus EA, that is 4. And the next voltage is this one EC, and then minus EB, which I will call this 6. Okay. So, here I have 1, 3, 5 as it is, and the connected voltages are EA, EB, EC as it is. Now, come to the second basic commutation group. So, what I will do is I will interchange the positions of the thyristor valve and the voltage source. So, I will first put the voltage source, and then the valve. Right. Now, there are 3 parallel paths. So, there are 3 voltages minus EA, minus EC, minus EB, and thyristor valves 2, 4, 6. Okay. So, one of the voltages is minus EA. So, I will show minus EA. Suppose this is minus EA. See, minus EA is appearing in the first circuit as the second branch, second parallel branch, but I am showing it in as a first branch because all these are connected in parallel. Okay. So, what is connected in series with minus EA? Which thyristor? 4. Then there is a voltage minus EB, and the valve that is connected in series with minus EB is 6. And there is a voltage minus EC, and the valve that is connected in series with minus EC is 2, and of course, the voltage across the 2 DC side terminals is VD. Okay. Now, I say that the second circuit diagram is equivalent to the first circuit diagram. The only change is in the second basic commutation group, I have interchanged the positions of the valve and thyristor valve and the voltage source, that is all. Okay. Now, how does that matter? Okay, let us see how does this matter. So, for that I need to draw one more equivalent circuit. So, I will retain the circuit of the first basic commutation group as it is. So, I have thyristor valves 1, 3, 5, and they are respectively connected in series with the voltage sources EA, EB, EC. Now, if you look at the second basic commutation group, which consists of thyristor valves 4, 6, 2 connected in series with minus EA, minus EB, minus EC respectively. Now, take the thyristor valve 4. The cathode of 4 is connected to the negative terminal of minus EA. Okay. So, let me give some name. Suppose I call this terminal as say terminal A. I call this terminal as say terminal B, I call this terminal as say terminal C, some names uppercase A, B, C I have used. Okay. Now, what is the potential of terminal C with respect to terminal A? See, minus EA is the potential of A with respect to C. Minus EA is the potential of A with respect to C. What is the potential of C with respect to A? EA. So, that is as good as the potential of B with respect to A. So, that means B and C are at the same potential. I will repeat, potential of A with respect to C is minus A, because plus is at A, minus is at C. So, potential of A with respect to C is minus EA. So, potential of C with respect to A is negative of, that is EA. So, that is nothing but the potential of B with respect to A. So, that means B and C are at the same potential. So, that means even if I short B and C, the circuit will work as it was working originally. So, what can I do? I can actually eliminate one of the sources. See, there is no point in connecting two voltage sources in parallel. Two equal voltage sources in parallel, I can just reduce it to one voltage source. So, what I can do is connect this cathode of thyristor valve 4 to B directly. So, what I see, this is B. So, I take this terminal B and connect it to the cathode of 4. Is that okay? Now, a similar explanation can be done even for the second path and the third path. So, I can say that this is equivalent to connecting this terminal, positive terminal of EB can be connected to the cathode of thyristor valve 6. And the positive terminal of EC is connected to the cathode of thyristor valve 2. Is this okay? So, the two DC side terminals are brought out here, the voltage across the DC side is VD. Now, what did we achieve by doing these manipulations? See, though these circuits contain voltage sources, in practice they are EMFs induced in the transformer windings. So, they are transformer windings. Now, by getting this third circuit, see I started with the original circuit, in the third circuit you see 3 voltage sources, in the original circuit there were 6 voltage sources. It essentially means I can show that a circuit with 6 transformer windings is equivalent to a circuit with only 3 transformer windings. So, I do not need 6 transformer windings, I need only 3. So, what will be the effect on transformer utilization factor due to this? It gets reduced by how much? Yeah, it is tempting to say half, but the number of windings get reduced by half, but the current rating, what about the current rating? See, I have reduced the number of transformer windings, but by reducing the number of transformer windings, what is actually happening here is current rating increases, but what was the wave shape of the current through the individual transformer winding? It is a constant for a certain duration equal to ID by R, and for the rest of the time is 0 if you take any one cycle. See, the waveform is like this. Suppose so, if I take one cycle, so I can always find a value C such that the wave shape of the current through the transformer winding is like this, where it is equal to ID by R for a certain duration and it is equal to 0 for the rest of the duration in the period. So, this duration is in the original circuit, I am talking about the original circuit. 2 pi by q, okay, 2 pi by q. Okay. So, suppose I take the current here as I. Now, suppose I take the revised circuit, I take the current here as say I prime. I prime. So, current rating of each transformer winding increases by a factor of root 2. Now, I am talking about this circuit, the current rating of each transformer winding in this circuit, in the last circuit that I derived. For this circuit, TUF is equal to the value that was obtained. So, the value was 1.481, 1.481 divided by root 2. So, there is a reduction in the transformer utilization factor. So, this is possible by manipulating the circuit. So, what is this circuit? I mean, are you familiar with this circuit? Yeah, this circuit has a name, it is called gate circuit. Maybe there are many sources which start from this circuit, but this circuit is not obvious. See, what we started with was an obvious circuit. We started with one thyristor valve, one AC voltage source. Okay. Then we tried to connect many such things in parallel, then many such parallel combinations in series, many such series combinations parallel, so on. So, what we started with something which was obvious, but gate circuit is not something obvious. I mean it is not obvious why it should work. Okay. So, actually gate circuit is derived, it is not something which will come just at once, So, gate circuit is in fact derived from something which is more obvious. Okay. So, normally it is not drawn this way. I mean, if you try to look at this circuit, I mean this is not the way in which it is drawn normally. So, we draw it like this. So, we show what is known as a leg. So, there are 3 legs. And there are 3 voltage sources. So, this voltage is EA. So, I am just redrawing the circuit that we just now obtained. So, these 3 voltages are EA, EB, EC, and they are displaced by 120 degrees, and the name of this thyristor valve is 1, this is 3, this is 5. What about this one? This is 4, 6, 2, and I have a DC side with 2 terminals, the voltage across the DC side is VD. So, this is how it is drawn usually. So, this is the gate circuit which can be derived from a circuit or combinations of circuits that are more obvious. Okay. Now, this is a very ideal circuit because the transformer EMFs are shown as voltage sources, but in practice there is something which we can't ignore, that is the leakage inductance. Okay. So, many times we will consider the circuit. So, I will go to the next page. Our converter circuit for P equal to 6 is just this. So, I have 3 legs, So, the converter consists of just 6 thyristor valves. So, 6 thyristor valves form the converter, and you can easily see that there are distinguishable AC and DC sides. The 3 wires on the left form the AC side, and the 2 wires shown on the right form the DC side. So, what we will do in this course is we will assume that the AC side, that means whatever is connected on the AC side has a simple circuit, and there is a circuit for what is connected on the DC side. So, we will start with some very simple circuits for what is connected on the AC and DC sides as far as this course is concerned. So, we will assume that the AC side is represented by a voltage source in series with an inductance in each phase. So, there is an inductance L in each phase, and of course, a 3 phase balanced voltage source EA, EB, EC. So, 3 phase balanced sinusoid. Now, one should note that this converter is only this much. See, when I say converter, I am only talking about this for the time being. Whatever is in this red dashed line is the converter. And whatever I have shown beyond this is the representation of what is connected on the AC side or DC side. Now, on the DC side, as far as this course is concerned, for the time being, we will assume that there is a very large inductor on the DC side. So, the inductor will act as a filter for the current. So, due to which the current is a constant. So, current is constant means I can just represent the current by a source. So, I will call this current ID. Of course, there is a voltage here Vd, the voltage, instantaneous voltage is Vd, but the DC side is represented by a current source. So, we will spend a few classes on analyzing this particular converter. So, please note whatever is marked in the red dashed box is the converter, and the current source on the DC side is a representation of what is there on the DC side, and a voltage source in series, the 3 phase voltage source in series with the inductance L in each phase is a representation of what is there on the AC side. What exactly comes on the AC side and what is there on the DC side, let us come to that much later. Now, for the sake of simplifying our analysis, we will make a very simplifying assumption of these circuits on the AC and DC side. Now, we will spend some time on this, but we will spend just one class or at least slightly more than that on a much simpler circuit for the sake of simplicity. We will start with for the sake of simplifying the first circuit that we analyze, we will make L equal to 0. So, if L is equal to 0, the circuit becomes even more simpler. Okay. So, we will of course, we will consider L, but we will start with a very simple case L equal to 0. So, if L is 0, then there is only voltage source on the AC side. So, you see that there are 6 valves, but we as I mean as we know from the previous explanation, there are two basic commutation groups. See, valves 1, 3 and 5, they form one basic commutation group, valves 2, 4, 6 form another basic commutation. So, this basic commutation group consisting of valves 1, 3, 5 is called upper commutation group, upper commutation group. And valves 2, 4, 6 form the lower commutation group. So, at any instant only one of them is conducting. Now, please note this is in agreement with the original circuit, which was very simple. I mean, there was only voltage source and thyristor valve. Now, just in the previous circuit I had showed inductor also. So, there is an inductance L in each phase, but the presence of an inductance makes the circuit complicated. So, if there is no inductance, as in this case, at any instant there is only one thyristor that conducts among 1, 3, 5, and at any instant there is only one thyristor that conducts among 2, 4, 6. Okay. So, there is some instant at which the transfer of current happens from one thyristor to the other in the same commutation group. So, the transfer of current from one valve to the other is known as commutation. Okay. So, we use the word commutation to mean transfer of current from one valve to another in the same group, in the same commutation group. So, this is called commutation. So, the word commutation is actually used to mean this. And there is a term known as commutation voltage. So, we will be using this many times. Commutation voltage means that is the voltage which appears across a valve at the instant of turn on. So, voltage that appears across a thyristor valve at the instant of turn on. So, that means each thyristor valve has a commutation voltage. That means there are 6 thyristor valves. So, there are 6 commutation voltage, one for each. So, we will start with this simple circuit. We will try to analyze this in the next class. So, there are a few things to be talked about in this circuit. So, once we are through with this circuit, then we will go on to the next circuit with inductance.